So this is the third lecture by Harvey Friedman on invariant maximality and choice. Please.
I was just looking at the chat. Now I have to get rid of it. Sorry. Yeah.
Okay.
Okay. So this is lecture 3 out of 12. And now, for the first time, we're going to talk about the statements that we're going to prove are equivalent to consistency of large cardinals. So the six, I have a lot of variants for various purposes, but there's six of them. There's six of them that I call the lead statements. And the reason I call them the lead statements is that they are, in one way or another, arguably equivalent in terms of their transparency and clarity to various wide mathematical audiences. Some more readily than others and it depends on the audience, but they're all quite reasonable for various audiences. Then there are many variants that are introduced for various reasons, and I will also discuss those. But once you keep in mind that there are these six lead statements. All right. So now, why am I not getting a scroll here? Just a second here. Oh, here we are. There we are. These six lead statements are provably equivalent over RCA naught, but so are a whole bunch of others. So there's a whole five of them are provably equivalent over RCA naught. There's one that by elementary methods. There's one that's stronger that is not clear how to show its equivalent over RCA naught by any elementary methods. However, we do know that they're all equivalent over WKL naught because of the reversals. So morally speaking, everything here is equivalent. All these different forms are equivalent. All right. One of them, you will see, one of them is the strongest one of the six. And that one is the one that I do prove in lecture 5. So that automatically gives me all the rest. But that, of course, proof uses large cardinals. In lecture 4, which is the next lecture, in lecture 4, I'm going to prove weak forms of this statement in HCA naught prime, in Z3, and in Z. So we won't be talking about large cardinals at all in the next lecture. We'll just be talking well within ZF. Now, there's a great deal of mathematics that has the following general shape. Every widget has an associated gadget. Every widget has an associated gadget. You can think of all kinds of mathematics of this kind. Now, in many contexts, not all, but in many contexts, every widget has an associated gadget is rather barren. It might even be trivial. And you will want to go to something like every widget has a maximal associated gadget. Every widget has a maximal associated gadget. All right. Now, in our context, we will see that even the maximality doesn't give you anything of logical power. The statement is still provable in RCA naught. and we can effectively pass from the widget to the maximal associated gadget in most cases by an effective functional. Now, the next move that we make weakens the statement. The next weakens the statement to triple star. The weakened statement is every invariant widget has a maximal associated gadget. Every invariant widget has a maximal associated gadget. In other words, you put an invariance condition on the widget. And the invariance conditions is very simple, and we use the same invariance condition throughout the entire book. For the widgets, the invariance condition for the gadget will vary, but I use just one for all the lead statements. In fact, the invariance condition for the associated gadget that I will be using is essentially the same, falls under the interval shift invariance of lecture 2. The interval shift invariance of lecture 2 actually drives the entire book. Well, sorry, I shouldn't say that. Drives much of the entire book, and it drives all of the 6 lead statements. All right, now the invariant widgets are identified by finite information, and a maximal associated gadget is suitably computable. One can show in each case that that if you have an invariant widget, then you can find a computable maximal associated gadget. And this is provable at this level. This is provable in EFA, in very weak fragments of arithmetic. So we have something here. Every invariant widget has a maximal associated gadget. That's basically provable in EFA, and we're going to make a little change, and then it isn't provable without large cardinals. But here's a digression. There's some interesting computational complexity issues that arise that we're not going to address. Namely, if I have an invariant widget, how computable is the maximal associated gadget can be? So that becomes a somewhat interesting computational complexity question. We use, as I say, just one very natural notion of invariant widget throughout the entire book. This is order invariance, which I'm sure many of you are familiar with. So far, we've just stayed well within RCA, not even EFA, and now we introduce the second notion of invariance. So thus, we have a stack of 4 adventures here. We start with every widget has an associated gadget, which might actually be trivial. And then we have every widget has a maximal associated gadget, and that starts to get interesting, still provable in RCA naught. And then we have every invariant widget has a maximal associated gadget, which is weaker than double star, and which is entirely computable and provable in EFA. Provided you state the computability. So you don't have second order notions. In triple star, you won't have second order notions if you state it fully. And now we come to 4. Every invariant widget has an invariant prime maximal associated gadget. And this is what is the featured statements. They all have this form in the book. And again, I use different invariant primes, but I use the same invariant prime as I used in the second lecture for the lead statements. This so-called shift, this interval shift invariant stuff. All right, now we're also going to see that these statements number 4 star, actually all of them, but the important one is 4 star for what I'm about to say, is actually implicitly pi 0, 1. meaning they're provably equivalent to the consistency of SRP over WKL naught. In fact, showing that they're implicitly pi01 is an elementary argument, an exercise in undergraduate logic. Nice exercise in undergraduate logic to prove that these statements on a 4-star are in fact implicitly pi01 is a pretty use of Gödel's completeness theorem. But the fact that it's implicitly pi01 doesn't mean it's equivalent to con SRP. That requires substantial work. All right. Now, the invariant prime here falls under, as I said, the interval shift invariance notion we discussed in lecture 2. Now, in lecture 2, we discussed it mostly in connection with piecewise linear and semi-algebraic sets. And here we're using it more generally. I mean, less specifically, okay, so to speak, less specifically. All right. Now, okay, so if we just use shift invariance, which is, if we just use shift invariance for these statements, then you'll see that the statements are provable in ACA. I shouldn't have said ACA naught because it's actually better than that, the weaker system here. Just a second. Let's see if I can get this to be illegible. No, it's not working. This is ACA prime. I can't. Oh, well, maybe I can do something here. Put it up there. Yeah. Okay. Right. Good. ACA prime. This is the statement that for every n you can do n Turing jumps, starting with any subset of omega, where n is a variable, not a numeral. It's a variable. All right. The move to interval shift invariance causes double 4-star to have the strength of large cardinals. Now we shall see that the stars are trivial and immediately go to the double star. So here are the statements with double star. Here are the maximality statements. There are 6 of them. Every subset of, now you know what my widgets and gadgets are, by the way, just by looking here. Every subset of Q0n to the 2k has a maximal root. A root of, and it's on the bottom of the page, a root in an even dimension just means half, you're in the half dimension and the square is contained in the set. So maybe I'll just, there we are. Isn't that nice? That's the root, or square root if you like. I call it just the root. Okay, so every subset of Q0n to the 2k has a maximal root. Obviously has a root. The empty set is a root. So we want a maximal root. And it's surprising in some ways. All right, well, we're not getting to, we're just talking about general subsets now. Okay. Every subset of Qn to the k has a maximal emulator. Now, this statement sticks out a little bit. This is not quite like the others. It's like the others in many ways, but it's not quite, because I can't explain to you what an emulator is without talking about the first notion of invariance that we use. In other words, I have to tell you about order equivalence. So emulators, the notion of emulator depends on the notion of order equivalence. I don't have a version of max emulator that doesn't involve order equivalence, or at least there is. It would be a little awkward. It would take us off the track we want to go. So we'll postpone talking about what an emulator is. All right. Now, every reflexive symmetric relation has a free choice function. This is another interesting widget gadget. A choice function is just the obvious, and there's plenty of choice functions because the relation is reflexive. So the identity map is obviously a choice function, the identity map. But that doesn't mean that the identity map is what's called free. So a free choice function means that any two values of the function that are distinct, any two distinct values of the function are not related. That's what a free choice function is. And this is a pretty theorem. Every reflexive symmetric relation has a free choice function, but it still is provable in RCA naught. And this is why I call the book Invariant Maximality and Choice. Otherwise, without this, I called the book Invariant Maximality. And I get some mileage out of this choice-free thing because it turns out to be the right way for me to give the finite forms. The explicitly pi 0, 1 sentences that we'll get to in lecture 12. The explicitly pi 0, 1 sentences. The next one is every relation has a maximal free set. And a free set is a set such that any two distinct elements are not related. The next one is every graph on Q0 into the K. And by graph, I just mean simple graphs, no multiple edges. You can have a loop. So this notion of graph really is uses any edge relation. But it can't be reflexive. It has to be irreflexive. Yeah, sorry. Simple graph. Yeah, I mean, there are no loops. Sorry, back up. No loops and symmetric. That's what a graph is. Irreflexive and symmetric. Yeah. So every graph has a maximal clique. Very familiar. And then finally, the multiple version of max root. Every subset of Q0n to the mk has a maximal m root. And that just means that it's, what is an M root? I want to be careful. Yeah, that's a k-dimensional set whose mth power is contained in the set, in the original set. So a root is a two root. I put this last one in because it seems to be more powerful in the elementary sense. Now, again, I can show all these are equivalent by passing through my reversal, but it isn't so clear. It might be it may well be doable, but it isn't so clear how you get multi-root from root or any of the others. But the other five you can get with each other, and I do that in chapter 2 of the book. Sorry, chapter 3 of the book. This lecture, by the way, is about chapter 3 of the book. Yeah. And so is the next 2 lectures about chapter 3. Chapter 4 is the reversals, and chapter 5 is the finite forms. So, but the proof of any of these things without with obvious modifications, nothing special, automatically does multi-root. And multi-root obviously implies root, and then I'll indicate just a little about how you prove the other 5 are equivalent. Yeah. The one that's hardest, probably the one that's trickiest to prove is equivalent, is choice-free. One has to do something there. Yeah. Oh, I'm sorry. By the way, when I say equivalent, I'm talking about the form when I put invariance all over the place. Invariance in the second condition. Yeah. These are all equivalent to each other because they're all provable in RCA naught. So let me back up. When I was talking about equivalences and so forth, I was talking about the next round. This round, they're all equivalent to each other because they're all provable in RCA naught. All right. Sorry about that. Now, maximality, in each case here, maximality is just maximality under inclusion, nothing else. I told you what choice free was. I don't know why I repeated max free. I did that by mistake. In max free, free set means no two distinct elements are related. Max clique, I already told you all this. Emulators involve order equivalence. All right. Now, all these statements are proven RCA naught. Obviously, these resonate to different audiences. If you go back, you can actually see the audiences possible. Max Root, I think, has the widest immediate appeal for professional mathematicians. You just have a set in 2K dimensions. You want to find a K-dimensional set whose square is contained in it. The second one is the one that appeals most and maybe the only one that really would work in the framework of gifted high school. So I taught in gifted high school program, Arnold Ross program, a form of this. I didn't do arbitrary dimensions or n was one. You know, it was watered down, but it was communicable because it's sort of more direct in a way. It's very hands-on. So that one is for gifted high school more. This one, I would say, I think people in some form of geometry and topology probably would like this the best. It's not that it's so related to their work. It's just what would resonate. The next one, maximal free set, sounds like combinatorics, general combinatorics. Max clique, obviously graph theorists. That sticks out, graph theorists. And then the multi-root thing is just like the root one, except that we're introducing an extra parameter, integer parameter. All right, so I try to cover a lot of different bases this way. All right, now the invariance condition we're going to use for the widgets is just order equivalence, order invariance coming from the order equivalence relation. The order equivalence relation is OE. And since I'm doing this in arbitrary dimensions, I like to have one relation where I'm taking I'm applying it to subspaces, so to speak. And so I look at the space Q less than infinity, which is the space of non-empty finite sequences from the rationals. Q is the rationals. And the equivalence relation of order equivalence is that the lengths are equal and that they're in the same order. Very fundamental idea. OT of K is the number of equivalence classes. So OT stands for order type. Order type of K is the number of equivalence classes of this equivalence relation OE restricted to Q to the K. The OT of K is intensively studied, called Fubini numbers. It's the number of ways K competitors can rank in a competition, allowing for the possibility of ties. And it doesn't have to be people, it can be horses, horse races. And that's the phrase that's used to define it from Neil Sloan's favorite integer sequence archive, which I think many of you are familiar with. 1964 it was started. So these are very famous numbers. They come up in many different contexts. And we use them here a lot. Incidentally, OT of K is asymptotic to K factorial divided by 2 log K plus 12. And here is how they grow. Here is some sample numbers. Oops. Now, the number of equivalence classes, okay, sorry, the number of order invariant sets. So order invariant means union of equivalence classes, or the other way of defining it is X is an X if and only if Y is an S. X is an S if and only if Y is an S. That's the definition of order invariant. And Q of 0 n just means the interval, the closed interval 0 to n intersect Q. Just the rationals in the closed interval. The number of order invariant sets is 2 to the order type of K. And since I'm going to be working, quantifying over all the order invariant sets in 5 out of 6 of these statements, and the other one I'm doing essentially the same thing, but we'll come to that. I'm interested in the number 2 to the OT of K. And if I wanted to do anything by inspection, I have to deal with 2 to the OT of K inputs, right, for these things, right? Because there are a lot of order invariant sets. So notice that 2 to the OT of K is a perfectly reasonable number until you get to OT of 4. 2 to the 75 is not that reasonable. And that corresponds to my statements in 2 dimensions. Remember, I'm going to be doubling the dimension usually. All right. So now let's look at these weakened statements where I used order invariance. Every order invariant subset of Q0n has a maximal root. Just the same thing as before. Every finite subset of Q0n to the K has a maximal emulator. By the way, you can easily prove that the infinite case of the second statement here is the same as the finite one. There are only finitely many elements that could have any effect because there are only finitely many order types in a given dimension. So fin is this really doesn't do anything to this statement. Max emulator. But over here, OI max root changes the statement. You know, it makes it weaker. It's no longer bold-faced, right? It's light-faced. OI max root. Now, OI choice-free, every order invariant reflexive symmetric relation has a free choice function. And then OI max free, OI max clique, OI max multi-root. Now, don't get fooled. An order invariant object here can be extremely complicated. Surely not as complicated as an arbitrary subset of Q0n to the 2K or Q0n to the K. Well, relation, sorry, in a third case. In every case, we're talking about 2K dimensions for the input, for the hypotheses. except the special case of the second statement we have to talk about. For each one of these cases, you can find a computable, the conclusion can be made computable. And this is done by an obvious greedy argument. In each case, like, for example, look at the most, maybe the easiest one, OI max free. You line up the k-tuples and you continue to put them in if you can get away with putting them in. In other words, keep the thing free. And then at the end, you have a maximal free one, because if it wasn't maximal, why didn't you throw something in there, right? Okay. So all of these are proved. I guess maybe the trickiest one definitely is OI choice free. To do that one. But we're now ready to tell you what emulators are. So an emulator, let's see, I think I don't have this down here. Yeah, here we are. S is an emulator if and only if every element of S squared is order equivalent to an element of E squared. That's what it means. S is an emulator of E if and only if every element of S squared is order equivalent to an emulator of E squared. This is the high school version, and this actually has some quasi-religious advantages. You see, E is somebody you may want to emulate. In other words, you want to have all pairs look like pairs from E. You don't want to you think that E has got the whole world understood, so you want to stay within the way E is. Now, you don't want to make all your one tuples elements of, okay. I mean, you want to make them order equivalent. So this is an interesting idea, the notion of emulator. And a maximal emulator means you do it, you grow as much as possible, staying within that constraint. All right, we use the obvious greedy algorithms. What is the computational complexity? As I said, this is an interesting issue, which I don't address. All right, now let's start taking the plunge into quadruple star. Okay, there's a thing called Z plus shift invariance. Z plus shift invariance just means that if I look at the numbers 1 through n minus 1, if I have a k-tuple from the numbers through 1 through n minus 1, that x is an S if and only if it's shift, x plus 1 is an S. That's what shift invariance means for Z plus. Now, that, of course, there's a stronger notion of shift invariance, namely for every x in S, x is an S if and only if x plus 1 is an S, not just the ones in the integers. I write n minus 1 because I don't want to go outside the space, right? So, but that's a whole different can of worms. In fact, everything in this book is false for shift invariance. That's much too strong. Everything in this book is gone. We don't want to talk about shift invariance, too strong. All right. So I just call it shift invariance for SH for shift. So we have 5 statements involving just shift. This special kind of shift called Z plus shift. We're just going to shift the positive integers, not everybody. Okay, so this actually These aren't really that easy. They're not that easy to prove. You have to actually do something. And the real reason you have to do something is because of the endpoint n. Otherwise, it would be a special case of Ramsey's theorem, the whole thing. But the problem is that n is a different number. N is quite different than n minus 1. Because n minus 1 is inside and n is at the endpoint. All right. Now we're going to prove these 6 statements in ACA prime in the next lecture. So that was a little plunge. Now we're going to take a big plunge. Instead of shift invariance, we're going to allow a parameter, and the parameter has to be below 1. So 0, 1, z plus shift invariance is exactly like interval shift invariance of lecture 2. I mean, I changed some notation here. I was always writing out in lecture 2, I was always writing out the indiscernibles. Here, I just use a set there. But this is all trivial notational changes. The substance of it is exactly the same. Okay, so if I have something not just in 1 through n minus 1, but I have something also in the interval 0, 1, right open. So those are the parameters, so to speak. I don't shift those. If I just shift the bigger ones, the numbers 1 through n minus 1, and I leave the other ones alone, that's what this invariance is. So X is an S if and only if its shift is an S with these parameters fixed, with these and with these small numbers. All right. Now, what if it is in 0, 1 union? It's got parameters like, it's got parameters like 2.5. Well, then it doesn't count. I don't put any condition on that. So this is adhered. We're really falling under the interval shift invariance idea, which was done in the reals. Now, since we're working in the rationals, I can still pretend that these are the reals because it won't affect the statement. Since the original set is in the rationals, it's harmless to treat this interval as the real interval or the rational. It doesn't make any difference. Treat it as the real interval, because then I'm staying legally within lecture 2. I'm legally within chapter 2, where I did everything in the reals. So when I do everything in the rationals now, I can treat that as a special case, of the stuff in the reals. There's no difference in the way you can think of it. All right, so we have the following 6 statements. And we're going to prove all these statements using SRP plus, using large cardinals in not the next lecture, the lecture after it, the 5th lecture. We're going to prove some weak forms of this in well within ZF in the next lecture. Okay. So these are the official statements. This one is the lead of the lead. I had to pick somebody. This is the high school one. Although actually with high school, I had K equals 2, N equals 1. And the finite set was of cardinality at most 3. And that was enough for them. That was actually quite complicated, actually, to do that by hand, in RCA not. All right. So All right, now the multi-root version, of course, implies that all the others, as I said before, I'll say a little bit more about that. So we're only going to really be proving next time the multi-root version, because that handles all the others. And what I actually do in the book is I show the root version, not the multi-root version. The root version implies the other four. Put the multi-root version aside for a moment. The root version implies the remaining four, and then we prove that each of the remaining four implies the clique version, and then we prove that the clique version implies the root version, and then we've got a full circle. And these are elementary arguments, but they have to be done carefully. All right, in this way, we see that the 5 multi-root excluded are provably equivalent by elementary methods over RCA naught. Now, another variant is, what if I make n equals k? Well, it's not completely obvious that that's going to be equivalent, but morally speaking, you would think so. And I give a complete proof of that if you restrict to n equals k, you don't change the statements. I also have in the book the variant where I use a single space instead of all these spaces. But if I use a single space, I'm going to be using these fractions for the indiscernibility. We're going to have an invariance in the sense of the last lecture. -1, 0, right open, these fractions. But it's still just one space, q minus 1, 1. And that has some advantages to use, just use one space. I still advertise most heavily the original statements, the lead statements that have the multiple spaces. And this doesn't make any difference. You can prove equivalence. And even equivalence when you're strict to equal. And then for the reversal in lectures 6 through 12, I pick, since everything is equivalent I'm talking about, I'm free to pick any one of them, as long as it's not the multi-root thing. As long as it's not the multi-root thing, I'm allowed to pick any one of them. And I actually picked this one. Order invariant max clique -1, 0, -1, 0 shift. Having n equals k means this means one quantified variable. 1 QV means one quantified variable, which means I'm assuming n equals k. And then I'm using I'm indicating that I'm using this space. So that's what that means. I have this coded setup for, since I got so many variants, I need some good names for them, right? Even though they're a little bit ugly. And this statement reads every order invariant graph. And this is the graph one. So because it's clique here, see. Every order invariant graph on this space has an invariant shift, has a suitably, it's an interval shift invariant maximal clique. This interval with this shift, this interval with this shift, shifting along here. And this is one of the many equivalents that I'm talking about here. And this is the one that's the official one that I do the reversal on. Okay. This one is implied by everybody. Okay. Then there's something else that I do. And I guess I did, yeah, I'm going to tell you why this has turned out to be important. There's some stronger invariance conditions that I don't think are as natural for the mathematician as this one. This is the favorite one, because I'm using them for the lead statements. This one, because Z plus shift invariance is so clear, and I'm just adding parameters that are low down and not even part of this system here at all. So this is very basic. This one is stronger, and says that I can move around. So I'm allowed to move around the Z plus part. I'm allowed to move them around as long as they stay order theoretic. At least everything stays order equivalent. Now this one lower Z plus shift invariance is also pretty natural, but a little bit more involved. This means that I can use the interval 0, comma I, where I is between 1 and n minus 1, and then shift above. So instead of using parameters below 1, I can use parameters below 10. And as long as the numbers that I'm shifting are integers greater or equal to 10. See what I'm saying? It's the union of all those conditions. It's a conjunction of all those conditions. And this one is the same. This one is the same as this one, except that I'm allowed to move around the positive integers in any way I want, as long as the order stays the same. This is the strongest notion of invariance that I use throughout the book, the strongest. And I have a section in the book that proves that you can't use anything stronger. If you use something stronger, some horrible thing is going to happen to you. That this is optimal. There's a kind of optimality about this. That's why I wanted to consider these stronger ones, because this is not optimal. This one for sure is not optimal, but this one is optimal. So you get the strongest results this way. All right. Yeah, I just described to you all this. Yeah. Yeah, just what I said. And I call it lower order invariance. I call it lowered, and this is the strongest statement in the book. The strongest statement in the book is this statement, because I'm using multi-root and I'm using lowered. Okay, this is the strongest one, and I actually prove this for you in lecture 5. Gives you all the other ones. Now, all the statements we've discussed are seen to be implicitly pi01 via the Gödel completeness theorem. You might say, well, I mean, how low are these statements? They're implicitly pi01. That doesn't mean I'm not interested in explicitly pi01. In lecture 12, I will do that. But there's been some huge breakthrough in the last few days about this, which I'll mention at the end. Something major. All right. But anyways, here is, I'll just pick one of these. In fact, I'll pick the one that's the basis of the high school statement, and just show you how easy it is to show by an undergraduate exercise. I recommend it to your undergraduate logic class that this is a pi01 statement. So every finite subset of the space has a appropriately shift invariant maximal emulator. So I'll just sketch the idea. It's obviously a little technical. So you fix K and N for the number of indiscernibles, so to speak, with those fractions, and K for the dimension. And I use constant symbols for all the stuff that you see, and a binary relation symbol less than, and a K-ary relation symbol S. Remember, S is supposed to be a K-dimensional set. And I'm going to build a set of first-order sentences. I'm going to build a set of first-order axioms. Actually, finitely many first-order axioms, depending upon K, my choice of K, N, and the numbers U1, and the vectors U1 through UM. So here's what these axioms look like. Less than is a dense linear ordering with endpoints, -1, 1, and all the constants are increasing like they're supposed to. The second axiom says that you are an emulator. S is an emulator, meaning any two things are order equivalent to some things in the pair, some pair of things in the ground, and the ground was the U's. Okay. And we don't actually use the U's in the theory. How do I say this? We're just using the order types of the U's. You follow me? We're just using the order types of the U's. So this statement has nothing to do with the actual U's, right? And then the third is maximality. It says, if I attempt to add a new thing, that should be a not sign, by the way. I forgot to format this. If I were to add a new vector, then I would ruin me. It would ruin it being an emulator. Yeah. Or there exists. There we are. Ruining the emulator means it's an existential property, right? So that there's something in there that has ruined me. Okay. And then we have to actually say that this thing is shifted, this thing is interval shift invariant. This is kind of cumbersome, but you get the idea. You have to look at, you have an axiom for each pattern. By a pattern, I mean some coordinates are supposed to be from -1, 0, and the other coordinates are supposed to be positive integers, right? And then you just say that you have an if and only if for the invariance. The invariance is an if and only if. I mean, I've put more details than that in the book, but it's pretty clear in the lecture what that is. All right, now the point is that I claim that T of Kn U1 through Um has a model if and only if this statement is true. I'm sorry, let me take it back. This T of Kn U1 through Am is satisfiable if and only if the original statement holds for K and N and U1 through Um. Sorry, that's what I meant. And that's clear. Okay. So then the whole statement, universally quantified, holds if and only if for all K and N and U1 through Um, T of Kn U1 through Um is consistent, because consistency is the same as satisfiability. Okay, there are some issues involved in this argument will use WKL naught, but what about induction? So let's not get into this. There's a Herbrand thing involved here. There's a Skolem function argument. Let's not worry about this. Okay, but basically, this argument's within the weak-Koenig's lemma, because you need weak-Koenig's lemma to prove the Gödel completeness theorem, right? So you get that the statement is equivalent to the consistency of each one of these systems. You could actually make one giant system if you want. No, that's not advisable. Let's not do that. Okay, if and only if each one of the, so the statement is equivalent to, for every Kn U1 through Um, that is consistent. And that's obviously pi 0, 1. All right, let me close the lecture by talking about gifted high school students. So clearly, this is a special case. What I'm writing down here is a special case of the statement that we just were analyzing. Namely, every finite subset of Q minus 1, 1 squared has a maximal emulator. I don't mean emulator here. I've actually broke it down as a maximal S. Yeah, I didn't mean that. As a maximal S with the following condition. For all P in Q minus 1, 0, we have P0 is an S if and only if P1 is an S, right? That's my shift with the parameter P. 0P is an S if and only if 1P is an S, right? And 0, 0 is an S if and only if 1, 1 is an S, because that's also a legal shift, even if there's no parameter. So what I talked about in the high school is a Ross program, a gifted high school, is this statement. Now, I didn't dare try to prove this statement for them because the only proof that I have uses more than Z2. This is more than Z2 to prove this. I don't have a reversal for this, by the way. If you try to do this by exhaustion, you'll superficially run into 2 to the 75. You'll have to have a big collection of subsets. And actually, it's not 2 to the 75. It's a lot smaller. It could be like 2 to the 50 or 2 to the 40 or something. Yeah, but anyway, it's very large. And so for gifted high school, what I did is I proved this by hand. But I proved this by hand. I found out that it's already was several lectures and complications, but totally elementary for the case of 3. So if you have every finite subset of cardinality at most 3, then this is true. And that takes some work, but it can be done in RC and on. And you can construct explicitly the S's involved. But it's interesting how Z2 comes into play and more if you want to do this for all finite subsets of Q, 0, minus 1, 1, 2. Doing it for 4 seems like a serious issue. Cardinality 4 by a hands-on argument. All right, I think that I went 1 minute over. I apologize to Andreas for that.
No need for apologizing.